L'Hopital's Rule, Euler's Method, and Logistic Growth by Lucy, Emily, and Jasmine.
L'Hopital's rule is used in the solving of a fractional limit problem with the answer in an indeterminate form, namely 0 over 0 or infinity over infinity. We generalize these equations as the limit as x approaches a value a of a function f of x divided by g of x, in which both functions approach 0 or infinity. In these situations, L'Hopital's is used with the conditions that f of x and g of x are differentiable and the derivative of g of x is not 0, limit as x approaches a of f of x over g of x is equal to the limit as x approaches a of the derivative of f of x divided by the derivative of g of x. With this rule in mind, let us move on to some example problems. Example 1. Consider the differential equation d of y over d of x equals x squared minus 1/2 of y. Let y equals g of x be the particular solution to the given differential equation with g of negative 1 equals 2. Find the limit as x approaches negative 1 of g of x minus 2 divided by 3 of x plus 1 squared to the work that leads to your answer. We know L'Hopital's rule can be applied because the answer is an indeterminate form of 0 divided by 0. With this information, we can do the derivative of the numerator function and the denominator function, which is equivalent to the limit as x approaches negative 1 of the derivative of g of x divided by 6 times x plus 1, which also results in an indeterminate form of 0 over 0. Therefore, we can apply L'Hopital's rule again, which results in the limit as x approaches negative 1 of g double prime divided by 6, which is equal to negative 2 over 6 simplifying to negative 1/3. Example number 2. Find the solution to the limit as x approaches infinity of x to the power of ln x divided by x. We cannot solve the limit when x is to a power of x, therefore we must manipulate the equation and put it as e to the power of the limit as x approaches infinity of ln of x to the power of ln x divided by x, and solve the limit before plugging back into e. With this, we can solely focus on solving the limit as x approaches infinity of ln of x to the power of ln x divided by x, which after manipulation, we discover that it is in the indeterminate form of infinity divided by infinity. We apply L'Hopital's rule, which ends up as the limit as x approaches infinity of 2 ln x divided by x, again ending in an indeterminate form, and we apply L'Hopital's rule a second time, which equals the limit as x approaches infinity of 2 divided by x, which limits to 0. Don't forget, this is the natural log of the function, so we plug it into e to the 0th power, which equals 1. Example 3. Find the solution to the limit as theta approaches 0 of theta cosecant 2 theta plus tan theta. With this problem, we can use the reciprocal identities of trigonometric functions, thus manipulating the function to be theta divided by sine 2 theta plus sine theta over cosine theta. We combine the two fractions, and the limit as theta approaches 0 is equal to an indeterminate form of 0 divided by 0. We derive the top and bottom function separately, ending with the limit as theta approaches 0 of 1 plus 2 cosine theta sine theta divided by 2 cosine squared theta minus 2 sine squared theta. If we apply the limit of theta approaching 0, we end up with 1 plus 2 times 1 times 0 divided by 2 times 1 minus 1 times 0, which is equal to 1/2. Example 4. Find the solution to the limit as x approaches 0 of cosecant x times ln of cosine x. Again, we use trig identities to turn it into a function with an indeterminate form as an answer, and we do the derivative of the numerator function and the denominator function, which ends up with the limit as x approaches 0 of sine x divided by cosine squared x. Remember, we don't always have to apply L'Hopital's rule a couple times, so if you find the limit, it is 0 over 1 or 0. As an overarching summary, some common mistakes should be noted. L'Hopital's rule can also be applied to both one-sided limits and positive or negative affinity. Moreover, the indeterminate form may not be immediately present and the function might need to be manipulated in order to achieve a limit that possesses a solution of the indeterminate form. For example, trigonometric functions can be manipulated with reciprocal identities, and functions to the power of another function can be put as a power of e with the natural log of the function so that the limit is still balanced. One efficient way of determining if the function needs to be manipulated is if the limit is infinity to the power of 0, 0 to the power of infinity, infinity plus 0, or any values that seem difficult to determine as a real number. If the limit of the function becomes infinity, check for continuity on both sides of the limit approaching from the left and the right to determine if the solution is infinity or if it does not exist. If using the rule once still results in an indeterminate form, the rule can be applied multiple times until the limit is no longer in indeterminate form. Finally, the most fundamental mistake is to apply L'Hopital's rule to any limit of a fractional function. However, it is only applicable to those where the result is in an indeterminate form.
The next topic we're going to talk about is Euler's method. So what exactly is Euler's method and why do we use it? Euler's method is based off of tangent line approximations, where the derivative of y and an initial value is given. From there, a tangent line must be made to y, or the function, at the given point, and then that tangent line will be used to move only a portion of the way to the unknown value, or the step size. The step size is also known as the amount of units to move over by, which can be represented in problems in two different ways. If the problem says use Euler's method twice, 3 times, 4 times, and so on, then you must determine the step size for yourself. But how do you do that? Let's look at an example and figure it out. This problem says to use Euler's method twice to approximate y of 2, and it gives us the initial condition y of 1 equals 4, and the derivative function y prime equals 2x. We know that we have to get from x of 1 to x equals 2 in 2 steps, meaning that the step size has to be 1/2, as the only way to get to 2 from 1 in 2 steps is to increase by 1/2. Since we know the step size, let's use Euler's method. The tangent line to 1 is y minus 4 equals 2 times x minus 1, or y equals 2x plus 2. Now we plug in the next value, which we know by our step size is 3/2, or 1.5. y of 3/2 is equal to 5. Now repeat this with the point we found, 3/2, 5. Plugging in our next step size, 2, we get 13/2, or 6.5. To check if we did this successfully, let's see if we followed the problem. Yes, we did use Euler's method twice, and yes, we approximated y of 2. Finally, we should discuss why exactly we use Euler's method. Although tangent lines are useful, they aren't very accurate, so Euler's method utilizes multiple tangent lines in order to get a better approximation.
Now we're going to move on to logistic growth, which is section 9.4 in our textbook. We know that population growth sometimes briefly resembles an exponential growth function, but when we take carrying capacity into account, we get more of an S-shaped curve. We can express this relationship as a logistic differential equation, as shown here. We know that dp dt represents the population growth rate. In this equation, capital K represents carrying capacity and lowercase k represents the rate. We have 1 minus p over k because if the population exceeds the carrying capacity, the 1 minus p over k will become a negative value, so the dp dt will become negative, and the population will decrease to get back to the carrying capacity. Since this is a separable equation, we could go through the long process of finding p of t, the equation for population. But as long as we know how it works, we can usually just go ahead and use this equation. It's also useful to know that k over 2 is the point of inflection and the population value at which we have the highest growth rate. Now let's look at our first example. The Forest Service ecologists have determined that a national forest can sustain a maximum population of 900 deer. When the forest is first designated as a wildlife preserve, there are 100 deer. 2 years later, there are 140 deer. Part A asks us to write the equation that models the population of deer in the national forest. Part B asks us what the deer population will be at time t equals 5, and it asks us to round to the nearest deer. Part C asks us, at what time does the growth rate start to decline? For section A, we're trying to find the equation that models the population. We know that the carrying capacity is 900, and we can solve for A by using this equation, k minus the initial population over the initial population, which will get us 8. Now we can plug those values into our p of t equation to get 900 over 1 plus 8e to the negative kt. Then we can check our point that was given to us in the problem, which is that at 2 years, there were 140 deer. Then we can solve for k to get 0.19388, and we can plug all the values that we found into our equation to get p of t is equal to 900 over 1 plus 8e to the negative 0.19388k. For part B, all we have to do is plug in 5 to our p of t equation that we found in part A, and we'll find that the population at time t equals 5 will be about 223 deer. For part C, we need to know that the point of inflection occurs when the y value is equal to k over 2. Now that we know this, we can set the equation to be 450 equals 900 over 1 plus 8e to the negative 0.19388t, and we can solve for t. Then we'll find that the growth rate starts to decline at time t equals 10.725. Now for a second example, the population of fish in a lake is growing fastest at time t equals 3, where t is measured in weeks, when there are 700 fish in the lake. The initial population was 200 fish. Part A asks us to write the logistic differential equation dp dt equals rp times 1 minus p over k for this scenario where r is equal to 0.012. Part B asks us to write an equation that models the population of fish at time t. Since we know that the population is growing fastest when p of t is equal to 700, that means that our point of inflection occurs when p of t is equal to 700. Since we know that k over 2 is equal to 700, we can know that the carrying capacity is 1400. Therefore, we can write the logistic differential equation as dp dt equals 0.012p times 1 minus p over 1400. Remember that 0.012 was given to us in the question. Now to find the population equation, we can just find A and K and know that our carrying capacity is 1400 from part A and find that the equation is 1400 over 1 plus 6e to the negative 0.59725t. Our third example is an FRQ from 2004. It says a population is modeled by a function p that satisfies the logistic differential equation dp dt is equal to p over 5 times 1 minus p over 12. Part A asks us, if p of 0 is equal to 3, what is the limit as t goes to infinity of p of t? It also asks us, if p of 0 is equal to 20, what is the limit as t goes to infinity of p of t? For part B, it says, if p of 0 is equal to 3, for what value of p is the population growing the fastest? For part C, a different population is modeled by a function y that satisfies a separable differential equation, and they ask us to find y of t if y of 0 is equal to 3. For part D, they asked us to find the limit as t goes to infinity of y of t, which we found in part C. For part A, we know that p of 0 is equal to 3, and the limit as t goes to infinity of p of t is equal to 12, and the same goes for p of 0 equals 20. This is because from the differential equation, we can see that the carrying capacity is 12. So as t goes to infinity, the population will get closer to 12. For part B, we know that the carrying capacity is 12 already, so we know that k over 2 is equal to 6. Therefore, we know that the population is growing the fastest when time t equals 6. Now for part C, they asked us to solve the separable equation that we had in the problem, which is dy dt equals y over 5 times 1 minus t over 12. Here, we need to separate the variables, put antiderivatives on both sides, and solve for y. Eventually, we will get that y of t is equal to 3e to the t over 5 minus t squared over 32. For part D, we know that limit as t goes to infinity of y of t equals 0. This is because t over 5 is being subtracted by t squared over 32, and when t goes to infinity, the exponent will be a large negative number. Therefore, the e term will go to 0 as t approaches infinity, so we have 3 times 0 is equal to 0.
We hope this video was helpful and informative. Thanks for watching.